In the South Bethlehem forge shop, the 35-ton hammer ram dropped, and what happened was not quite a sound. It was a physical event that traveled through the foundation timbers and was recorded in building walls a quarter-mile away. The men within 10 feet felt it in their chests and in their skulls. Bethlehem's own doctors wrote that down in the medical records by 1905. They documented progressive hearing loss attributed to hammer noise, but nothing changed for 64 more years. This is the story of the Nasmyth hammer at Bethlehem Steel and the men who ran it. If you are new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country, and the things those things cost. Subscribe now and leave a comment with the next story you want us to dig into. To understand why Bethlehem Steel had the largest forge shop in North America by the 1890s, you have to understand what forging is and why it was the only way to produce. A forged part is not cast, and it is not rolled, it is worked. A heated steel billet, brought to a temperature where the grain structure of the metal is plastic and responsive, is struck under controlled force in a sequence of blows that compress and reshape it. Each blow closes internal voids, aligns the grain structure along the lines of stress the finished part will experience in service, and produces a material property that neither casting nor rolling could replicate. A cast axle is brittle in ways a forged axle is not. A rolled section has directional grain properties that do not suit a rotating shaft. Every axle on every American locomotive, every drive shaft on every American ocean-going vessel, every piece of gun and armor plate that went onto a United States Navy battleship in the 1890s required a hammer forging. There was no substitute process. But the scale of American demand by the 1880s was something the forges of a previous generation had not been built to supply. In 1839, a Scottish engineer named James Nasmyth was handed a problem that the existing technology could not solve. The engineers building the SS Great Britain, the first ocean-going screw-propelled iron steamship, needed a wrought iron paddle shaft of a diameter that no tilt hammer in Britain could produce. Tilt hammers, powered by water wheels and limited in their ram weight by the structural constraints of timber framing, topped out at a few hundred pounds. The Great Britain's shaft blank required something an order of magnitude heavier. Nasmyth's solution arrived quickly. He sketched the principle of a steam-powered hammer in an afternoon. A piston and cylinder mounted vertically above an anvil block, the piston rod connected directly to the hammer ram. Steam admitted below the piston drove the ram upward. Steam admitted above the piston, or the ram's own weight with steam exhausted, drove it down. The operator controlled the blow energy by varying the steam admission and the drop height. The principle was so clear that Nasmyth reportedly demonstrated the drawing to visitors before the machine was built, and they understood immediately what it would do. The principle was genuinely self-evident in a way that distinguishes a few inventions from most. You looked at the drawing and you understood what would happen when the steam was admitted and released. The elegance was in its completeness. The same steam that lifted the ram also controlled its descent, and the operator at the valve had fine control over a machine whose raw force was enormous. The first Nasmyth hammer was operating in 1843. Within a decade, steam hammers of increasing size were running in British and Continental ironworks, and within 2 decades, the design had been adopted in American ironworks from New England to Pennsylvania. The machine scaled in a way that no previous forging technology had, and each step up in ram weight opened a new category of work that had previously been impossible. The principle scaled directly. A heavier ram, a larger cylinder, more steam pressure, and the hammer could work material of a size and weight that had been simply inaccessible to any existing forging method. By the time American ironmasters were placing orders in the 1870s and 1880s, the Nasmyth hammer had become the foundational machine of heavy forging everywhere in the industrialized world. But what American industry needed by then was not just the machine as Nasmyth had designed it. It needed the machine at a scale that Nasmyth's original drawings had not contemplated. Bethlehem Iron, the company that would become Bethlehem Steel, was founded in South Bethlehem, Pennsylvania in 1861 by a group of investors that included Joseph Wharton. It occupied a site on the Lehigh River with rail connections and coking coal within reach, and through the 1870s it was a mid-sized iron and steel producer competing in a market that Carnegie's Pittsburgh operations were coming to dominate. What differentiated Bethlehem from the rest of the American industry was not its blast furnaces or its rolling mills. It was a specific capability decision made in the late 1880s that the company pursued at a scale no American competitor matched. That decision was heavy forging for the United States Navy. The Navy's new steel battleship program of the 1880s and the 1890s required two things in quantities and specifications that American industry had not previously been asked to supply. First, forged steel armor plate, thick enough to resist naval gunfire, surface hardened by a process that required precise hammerwork at precise temperatures to achieve the right metallurgical gradient from hard face to tough backing. Second, forged gun forgings, the barrel blanks that would be bored and finished into the main battery weapons of pre-dreadnought battleships. Both products required hammers of a size that Bethlehem's competitors did not have and had not invested in building. The need for forged steel at scale reshaped Bethlehem's priorities. The Harvey process for face-hardening armor plate, which Bethlehem licensed and developed through the early 1890s, required that the armor face be carburized and then rapidly quenched after the final hammer sequence. The timing was precise, and the hammer work before the quench had to be exactly right because the metallurgical gradient that made the plate resistant to shell penetration depended on the final condition of the surface layers at the moment of quenching. This was not work that could be done on an undersized hammer with an operator who was still developing his reading of the billet. It required the largest hammers in the shop and the most experienced men on those hammers. Precision and experience mattered. The contracts Bethlehem won for the armor plate of USS Indiana, USS Massachusetts, and USS Oregon in the early 1890s were the foundation of the forge shop's reputation and the source of the capital that funded further hammer investment. By 1895, Bethlehem was the only American facility capable of producing the full range of forgings a capital ship required, from the keel forgings to the armor plate to the main battery gun barrels. The Navy's fleet expansion program ran on what came out of South Bethlehem, and the forge shop ran to supply it. Bethlehem invested. The forge shop that grew through the 1890s on the South Bethlehem site became the largest heavy forging facility in North America, equipped with hammers whose ram weights ran from the modest end of the production range up to the 35-ton class machines that handled armor plate and the largest shaft blanks. The anvil blocks under those hammers were seated on timber foundation grids designed specifically to absorb and spread the shock of a blow that, at full drop from a 35-ton ram, delivered energy equivalent to detonating several pounds of explosive at the anvil face. Could you imagine working the floor of that shop every day? Leave a comment below with what you think that must have felt like. The forge shop floor during an armor plate or axle production run was an environment unlike anything else in American industry of that era, and it is worth being specific about what it actually contained. The soaking pits ran along one wall of the forge bay, lined with refractory brick and fired to temperatures above 2,200 degrees Fahrenheit by gas or producer gas burners. The billets sat in those pits for hours before they were needed, soaking through to a uniform working temperature. The heater was responsible for the pit, for its temperature, for the rotation schedule, for reading the color of the steel in the pit, and knowing when a specific billet had reached the correct condition for the next hammer sequence. The heater worked closer to the pit than anyone else in the shop, in radiating heat that even at a working distance was enough to produce significant thermal load on the body over a 10-hour shift. When a billet was ready, the heater drew it out on tongs. In the largest class of work, this was not a one-man operation. A large shaft blank or armor plate billet weighed several tons, and moving it from the pit to the anvil block required a crane and a crew. The holder operated the crane controls or worked the secondary tongs that positioned the billet under the ram, reading the hammerman's hand signals for each repositioning between blows. A large forging required dozens of blows in a specific sequence, rotating and repositioning the billet after each strike to work the steel evenly and close the internal structure uniformly. The communication between the hammerman and the holder was entirely gestural because spoken words were not a reliable medium on the floor of a working forge shop. At the throttle valve stood the hammerman, and his job was a form of applied physics that no engineering school taught and no book fully described. He read the deformation of the billet with each blow, read the color change as the steel cooled, read the surface texture and the way the metal moved under the hammer face, and adjusted the blow height and energy sequence in response. Too light a blow and the steel did not close internally. Too heavy, too fast, and a billet that had dropped below working temperature would crack rather than deform. The hammerman working a Navy armor plate forging or a large drive shaft blank was making dozens of calibrated decisions per shift, each one based on experience accumulated over years on the floor. The experience took years to develop, and it was not transferable except by working the floor. Bethlehem could not simply replace a hammerman who left or was disabled. The pool of men who could read steel at 2,200 degrees through the lens of how it moved under a hammer blow and adjust the machine accordingly was small, and each man in it had invested years of his working life and his hearing in building that skill. The hammermen at the top of their craft at Bethlehem were irreplaceable in a practical sense, which is why the company paid them well and why they stayed on the floor long past the point where the medical record would have recommended they rotate out. If you are finding this as important as anything we have covered on this channel, go ahead and hit subscribe right now and leave a comment below with the next story you want to see. But the sound that environment produced is where this story turns and where the medical record begins. A 35-ton Nasmyth steam hammer delivering a full production blow is not a sound in the way a factory machine is a sound. A belt drive hums with a consistent frequency. A rolling mill produces a continuous low rumble that workers stopped registering after a week. A steam engine delivers a rhythm you could time. What a 35-ton hammer produces at the moment of impact is a pressure wave. The physics are closer to an explosion than to a mechanical noise. Peak sound pressure levels at the operator position for large steam hammers of the Bethlehem class have been estimated from documented measurements of comparable hammers made in later decades when instrumentation existed to record them at 130 to 140 decibels during a production blow. That is a number that requires some translation. The threshold at which a single exposure begins to damage the hair cells of the inner ear is around 85 decibels for sustained noise. At 120 decibels, a single exposure of more than a few minutes produces temporary threshold shift, the ringing and muffling that follows a loud concert. At 130 decibels, damage from a single exposure is measurable. At 140 decibels, one blow is a significant noise event. The hammerman at Bethlehem was not experiencing one blow per shift. He was experiencing hundreds. The hearing loss that resulted was not the sudden bilateral deafness of a single catastrophic event. It followed a documented pattern that the physicians of the era, when they bothered to measure it, described consistently. Progressive loss in the high-frequency range first, the frequencies of speech consonants and environmental warning sounds, then spreading downward as exposure accumulated over years. A hammerman who'd been on the floor for 5 years could still hold a conversation at normal volume in a quiet room. He could no longer hear the holder's signals without looking directly at him. A hammerman who had been on the floor for 10 years had lost enough of the speech frequency range that communication on the floor was increasingly by context and by reading faces rather than by words. The progression is in the records, but what those records document is not only a physiological fact, it is a gap between what the company knew and what the company did, and that gap is specific and measurable. Bethlehem Steel's company physicians began conducting systematic periodic physicals on forge shop workers around 1905. The records that have been located from this period document what the physicians found progressive high-frequency hearing loss in hammermen and heaters at rates significantly above what was recorded in workers from other plant departments. The physicians attributed the loss to hammer noise in their notes. The documentation was made, filed, and handled the way occupational medical documentation typically was in American industry from 1905 to 1915, which is to say it was not acted upon in any operational sense. This is not a story about negligence in any simple sense, and it is worth being precise about why the documentation did not produce action, because the reason is structural, and it repeats across American industry and in this period. Hearing loss was not a compensable injury under Pennsylvania workers' compensation law, as it was interpreted and applied in the early 1900s. The workers' compensation framework that Pennsylvania adopted in 1915 covered traumatic injuries with identifiable onset dates. A man who lost a hand to a rolling mill had a compensable injury with a date and a cause. A man who lost his hearing progressively over 8 years of hammer work had a physiological process without a legal event attached to it. The framework did not cover it, which meant the company's liability exposure from documented hearing loss was zero under the law as it stood. The medical records documented a real harm, but the legal structure did not require the company to respond to that harm, and it did not. The absence of a legal requirement was also the absence of any mechanism that would have produced a voluntary response. The forge shop workers were also the highest paid production workers at Bethlehem by a significant margin. The wage premium on the hammer floor was understood by everyone at the plant, including the men who accepted it. It was not a secret that the work was hard and that it cost something. What was not disclosed, because there was no mechanism that required disclosure, was that the cost had been measured, documented in the company's own records, and was progressing on a predictable trajectory for every man who stepped onto that floor. No standard hearing protection was issued in the Bethlehem forge shop during the period covered by those early medical records. Cotton wool in the ears was available, and some men used it. It provided perhaps 10 to 15 decibels of attenuation at the frequencies where it worked at all, which at a noise source of 130 to 140 decibels meant the difference between severe damage and slightly less severe damage. Purpose-designed industrial hearing protection did not exist as a practical, available product until the 1930s. It was not required as standard issue in American industrial workplaces until federal occupational noise standards took effect in 1969 under the Walsh-Healy Act amendments. The gap between Bethlehem's medical records, noting the problem in 1905, and the federal standard that addressed it is 64 years. The men who were examined by Bethlehem's physicians in 1910 and 1915, and who were told, or who were not told, what the examination found, continued to work the hammer floor for the duration of their careers. There was no mechanism by which the medical finding translated into a change in their assignment, their hours, or the equipment they were issued. The physicians documented what they found, the forge shop continued producing what the Navy and the railroads needed, and the hearing loss progressed through every shift in between. A man who started on the hammer floor at Bethlehem in 1900 and worked it through 1920 had accumulated 20 years of shift-length exposure to a sound source at the upper limit of what the human ear can tolerate before structural damage. By the end of that career, the high-frequency range was gone, and the mid-frequency speech range was compromised. He could still work the floor because he had learned to read the holder's signals by sight, but he could not follow a normal conversation in a room with background noise, and that condition was permanent, progressive, and had no treatment available to him. What the hammer floor produced during those 64 years, in terms of output, is documented in Bethlehem's production records and in the contract files of the United States Navy. The armor plate for the pre-dreadnought battleships of the 1890s, the propeller shafts for American merchant vessels in the early 1900s, the gun forgings for the Navy's expanding fleet through the first decade of the 20th century, the railroad axles in quantities that supplied the American rail network's expansion. All of it came out of the South Bethlehem forge shop, and all of it required the men at the throttle valves and on the tongs to be within 10 feet of a machine that was systematically destroying their hearing with every shift they worked. A railroad axle forging required a sequence of perhaps 30 to 40 blows across 2 or 3 heats, with the billet returning to the soaking pit between heats to be brought back to working temperature. A large armor plate forging required more. A drive shaft blank for a major vessel might require 100 or more blows across multiple sequences over the course of a full shift. Each blow was a pressure event at 130 to 140 decibels. The hammermen who worked the armor plate contracts were accumulating hearing damage at a faster rate than the men on standard production runs, because the armor plate work required more time at the throttle and more total blows per shift. But the medical records do not break the data down by product type. They record what they found, which was men going deaf, and what they attributed it to, which was the hammer. The men who spent careers on the Bethlehem hammer floor are in 2 kinds of records. The production records show their output, their department, their years of service. The medical records show what happened to their hearing. Neither record gives you a complete picture of what their working life was, and neither is easy to find now. The production records that survived Bethlehem Steel's bankruptcy and the demolition of much of the South Bethlehem site are in archives that require specific access. The medical records from the early 1900s, physician examinations, are partial and not fully cataloged. What those records, taken together, show is a company that was running the most important forge shop in North America, that employed men it paid well for extraordinarily difficult work, that had its own physicians documenting the physiological cost of that work in terms specific enough to identify the cause and the progression, and that operated for more than 6 decades between the first documentation of the problem and the legal requirement to address it. The hammermen who went deaf in the South Bethlehem forge shop between 1905 and 1940 are not in the public history of Bethlehem Steel. The public history covers the steel production tonnages, the Navy contracts, the role of the plant in 2 world wars, the labor battles of the 1930s. It covers what the plant made. It does not cover what making it cost the men who stood beside the hammers. The Nasmyth hammer worked exactly as James Nasmyth designed it. It worked forged steel from a plastic state into a finished shape with precision that no other process could match. It made railroad axles that did not fail, drive shafts that did not crack, armor plate that stopped shells. The men who ran it and fed it billets from the soaking pits and held the steel under the falling ram for 10 hours a day, 6 days a week, built the machines and ships and infrastructure that the country ran on for a century. What it cost them is in the records. The records were kept. Nothing changed until the law changed it. The Bethlehem hammer floor operated for decades, based on a documented medical record that showed exactly what the work did to the men who ran it. To keep following the stories of what the industrial era cost the people who built it, subscribe to Steel and Sweat.